Now, as you've probably guessed from this title, not all linear functions are just the familiar straight lines on a graph. Although we do point out that these special linear functions are still straight line segments. What's the difference between a line and a line segment? In theory, a line goes on forever. So a line segment has, well, it's basically from point A to point B, whereas a ray is from a point and on forever. Now, since we're working with line segments, well, one example is a step function. Why is it called a step function? It's because when you actually draw it, it looks like a staircase. So, a step function has a bunch of constant values. Now, it doesn't always have to look like this. It can go like this. With dashed lines to show how they jump. And if this end happens to be not included, then that means you have an open circle. If it's included, then you have a filled circle. Or alternatively, in some areas, the notation is open circle for not included and no signal for included. So you don't need to draw the filled circle. Now, a piecewise linear function, a step function is an example of this. Piecewise means that each little piece, each x interval, has a particular equation associated with it. So for example, this would be piecewise. Although, if you've ever seen a sine wave, that is not piecewise. It's also not a linear function, so the point remains that piecewise linear functions will have different equations for different sections. An absolute value function is an example of a piecewise linear equation. So, it looks more or less like this. It's a little bit off, but I hope the point gets through. Now, this has domain of negative infinity to positive infinity, not inclusive on either end. Inclusiveness is very important, because what's the range for an absolute value function? Well, it starts at 0, it includes 0, see, the square brackets is includes, and then this goes to positive infinity. Range is the range of values that the dependent variable can take. Domain is for the independent variable. Now we point out that if it's a function, then for every value in the domain there is one and only one value in the range. Otherwise it stops being a function. Example 1, write the greatest integer function f(x). f(x) is the greatest integer not greater than x. How do we find this? Well, let's say x equals n. So x is n to n plus 1. It does not include n plus, if it doesn't include n plus 1, then the fx is equal to n. But it can be equal to, x can be equal to n because it's not greater than x. That means less than or equal to. So it doesn't include n plus 1, which means we write this. And then n is an element of the real numbers. So this we will draw down here. Now I'm going to draw this a little bigger so that you can actually see what's going on. So you might notice that I scale it up to 2. So we have include n, but not include n plus 1, which means that here we will have an open bubble, and here we will have a filled bubble. And this dash line up, and open bubble, dash line up, and this is a filled bubble. So this is a stepwise function, also known as just step function. So this is piecewise, sometimes known as stepwise. And as you can see, it somewhat resembles a set of steps. We point out that, well, okay, first we should probably label all the scale parts. We point out that not all step functions have to look like steps. They can jump all over the place for all we care. But they are still functions. So for every value in the domain, there is one and only one value in the range. Outside the domain, on the other hand, well, who cares? It's something else. Because the domain may not end, or it might have ends, depending on the function. So we have to graph each function, state the domain and range. The first one is y equals x plus 2. Which means, well, okay, let's say this is 2, and this is 0, and this is negative 2, 2, negative 2, x, y. Or, technically speaking, since this is fx, we should write fx instead of y. So x plus 2. That means we need to have a slope of 1 and have y-intercept of 2. All right. So domain is x is an element of the real numbers. You might say have some other particular notation depending on region for real numbers. And range fx is an element of the real numbers. Now what about fx equals x minus 4? Well then, minus 2, 2, minus 2, 2, x, f of x. F of x equals x minus 4. That means we still have a slope of 1. There we go. So, domain x is an element of the real numbers, and range is f of x is an element of the real numbers. F of x equals 3x. Well, this would lead us to, we'll draw the scale in a moment. Two, negative 2, negative 2, 2, 0, x, y. So, yes. This is not supposed to be y, this is f of x. Domain is once again the real numbers. And range fx is an element of the real numbers. When is it that you have domain and range not something like this? Well, when they give you a particular domain, clearly the domain is going to be whatever they give you. Or, if it's like, oh, the function, well, not function anymore because it wouldn't be. The equation is x equals 3. Well, the domain is x equals 3. And of course, if the range is limited, then sometimes you end up with something like, oh, y equals 4. Well, the range is going to be set 4. Set. The brace brackets, or big brackets as some people call them, are used for sets. Now, graph each function, states a domain and range. Well, f of x equals, axes first, x plus 1. So now we choose a scale, and this is reasonable. negative 3, 3. You can choose to label your horizontal scale differently from your vertical scale. But do try to make it consistent if the graph is clearly centered on 0, 0, and, well, it wouldn't do to have minus 3 and 5. So, f of x equals x plus 1, absolute value. That means, well, wait a second. What do we have when x equals 0? Well, 1. And then at x equals negative 1, 0. And then from there back, it goes back up. Now, this should be a straighter line, but, well, these things happen. Domain is x is an element of the real numbers. And range is f(x). You can choose to write it this way. Or you could choose depending on teacher preference. Here we have f of x equals the absolute value of negative x plus 1. So, x and f of x. So say we have 3, negative 3, and 3, and, well, negative 3, and 3. And of course we have 0 as the middle. And negative x plus 1. So when x is 1, this is 0. And when x is 2, this is, well, this comes out to 1. And when x is 0, this comes out to 1. Since the absolute value is on the outside, it's not hard to find that it, depending on the point that it bottoms out at, and, well, okay, the slope also matters, because if this was, say, 3x plus 1, that would be different. But if you find the bottom point and the slope, well, these absolute value functions are drawn very simply. So, domain x is an element of the real numbers, and range is, well, f of x is, wait a second, we can do greater than or equal to 0, or f of x is, well, okay, so clearly it's inclusive of 0, hence greater than or equal to. So inclusive 0, and up to what? Infinity. Now some people prefer when you write positive infinity like this. Just be careful of what your teacher likes better. Alright, so here we have f of x is equal to negative x plus 4 if x is smaller than or equal to 1. Alright, 0, negative 4, 4, 4, negative 4, and x, f of x. Alright, negative x plus 4. If x is smaller than or equal to 1, that means, well, okay, if at 1 we would have 3, and then on back. Alright, so this is inclusive, which means that we need to use a solid ball here, depending on, of course, on regional convention. Some areas only mark where it's exclusive. So, x minus 2 if x is greater than 1. Well then, that means here we have 1, and minus 2 would be negative 1. And from there we go on up. Of course, we do note that we should draw a dashed line here to join these 2 points together. Otherwise, well, we wouldn't be able to denote the jump properly. And of course, sometimes you make little mistakes when you're drawing a diagram. Like say you're supposed to draw velocity versus time, and you draw something like this. Well, okay, it might not line up exactly, but as long as it passes through certain points on the scale, say 6 seconds, this is for physics class later on, or a science class for that matter. If it passes through these points, this line might not be completely straight, although really you should use a ruler for these things, but sometimes these things happen. So hence why the need for these dashed lines. Now, what's the domain here? Domain is domain. Since the domain joins together with this side being inclusive and that side not, then this domain is still x is an element of the real numbers. And the range is then, well, wait a second. What does this do? Okay, first we go up, and here we go up again. So the range is, well, not greater than or equal to, because this is not inclusive. It's strictly greater than -1. So f of x is greater than -1. Or we can use the more advanced notation, which is f of x is an element of the set -1, not inclusive, to positive infinity. Alright, so that's also not inclusive because you can't really include infinity. The concept of infinity is, well, infinite. It's endless. So that's actually it for some of these more special linear functions, linear equations technically, because sometimes they're not functions. Why? Why? Well, wait a second. If a function has any overlaps, like for example, it's a vertical line, that's not a function. That's a relation. So, for these linear equations, this is about it for the special cases. And I guess we'll see each other again next lesson then.